we've already looked at the function y equals 2 to the x. And you'll remember that what happens with 2 to the x, so when y equals 2 to the 0, that was 1. When y was equal to 2 to the 1, that was 2. Y equals 2 to the 2, that was 4. And you note that these values here, the y values, they double each time. So it started at 1, 2, 4, 8, 16, 32, 64, ... Well, what that represents in terms of an increase each time is in fact a 200% increase, okay? Now, why is it 200%? Well, if I've got 1 as the starting value and I multiply that by 100%, that's 100 over 100, which means that I'm left with 1, i.e. 100% means the same amount, or it's like multiplying by 1. If I multiply by 200%, that's 1 times 200 over 100, which in this case will be 2. So 200% represents a doubling. If I wanted to do, say, 1.5 times the amount that I previously had, that would be 150%, which would be 100%, so all of what I had before, plus half of what I had before. So that would be 150% in total. So that's how increases work. Now, if the average increase in house prices in the new millennium is 8% per year, what is the exponential factor? Well, that's starting to talk about our A value. So here, this thing here, base 2, in this case was the exponential factor. We're looking at an exponential factor to represent this scenario. Now, the exponential factor in this case is going to be 100%, which is all of the value of the house previously, so 100%, plus an extra 8%. Okay, so what we're doing is we're saying it's the previous year's value plus another 8%, which represents 108%, or 108 over 100, or 1.08. And that's our exponential factor. That's our A value here, 1.08. 1 represents all of the previous year, and 0.8 represents 8% also of the previous year's value. So price increased by 8% per year, that is, the price at the start of the year is 108% of the previous year's price. Therefore, our A value is 1.08. And what this is growth, which is what you want to have happen with your house, obviously. If you've bought a house, you want that A value to be greater than 0. You want it to appreciate or grow in value. Here's a number of situations where we're going to get the A value or try and depict these situations with an A value. So this is a 5% interest rate increase on an investment per year. So if I chuck money in the bank at a rate of 5%, what I'm going to get is all of the previous year's amount, well, so I should, plus another 5%, which equals 105%, which as a decimal, 1.05. So our A value there would be 1.05. Okay, this one is halving the value annually. So basically, if I invested 1,000, what would happen after 1 year is that it would be worth 500, then to 250, etc., etc. So what that represents is 50% of the previous year's value. So that'd be 50% or 0.5, and that's going to halve the amount. All right, a 30% discount on price of a pair of shoes. So what it would mean is I'm discounting those shoes by 30%. And then if I'm doing exponentially, it'll be 30% of the discounted shoes that were already discounted by 30%. Anyway, so 30% discount actually represents all of the previous price, subtract what I'm taking off. That is, I'm removing 30%. That means that the price of the shoes is actually 70% of the previous value, okay? So I'll just go over to the calculator to try and depict this, because this is one that students find a little complicated. So say, for argument's sake, I had a pair of shoes that were worth $100, okay? And what I wanted to do was to find out the price of the shoes after a 30% discount. Well, what I would do is multiply the 100 by 70 over 100. That is, it would have 70% of the previous value's price. So 70 over 100 means that the value of the shoes would be $70 after a 30% discount. So the most common mistake with this one here is I find students see 30% discount and say that the A value is 0.3, but it isn't. It's in fact 0.7. And that's the calculation that we need to do to get to this value here. All right, 12% annual depreciation in the value of a car. So cars are one of the worst investments you can make. They depreciate heavily, and this would be, say, an average depreciation of a car. That means that the car is going to lose value. Very rarely do you buy a car and then are able to sell it for more than it was purchased for. So that means that if it is a 12% depreciation, that is, it goes down by 12% each time, it would be 100% of its previous value minus this 12%, which actually represents 88% of the previous value of the car. So A value there would be 0.88. Again, the most common mistake is students write 0.12 as an answer. And again, have a look at this. If I bought a car for $20,000 and multiplied that by 12 over 100 or 12% of it, that would mean that after a 1 year, the car was worth $2,400. And I've heard of depreciation, but that's just crazy. Okay, if I bought a $20,000 car, I'd be hoping after 1 year it wouldn't be worth $2,400. Okay, so this one here, 37.5% markup in the cost price of goods. Again, to be topical at the moment, I've seen pictures of toilet paper being sold for extortionate rates in country places and more controversially in Indigenous communities. Some horrible price gouging, it's actually called, that's a technical term for it. But it's common for a business when they sell something to mark up the price or the cost price of what they get the goods for, obviously to generate a profit. So if they're doing a 37.5% markup, they want to sell the item for all of or 100% of what they bought it for plus 37.5%, which represents 137.5 or 1.375 as my exponential factor. Doubling the number of cells during mitosis. Wouldn't have a clue what mitosis is. Mr. Kruger would probably be able to answer that one there, but I presume it's some sort of biology thing there, or Ms. Downey, of course, the biology guru. But this one here, doubling, so if I don't know how many cells we start with mitosis, but maybe 2, that would double to 4, that would double to 8, to 16, etc., which represents 100% plus all of it again, which is 200%, or our A value 2. Okay, so now to have a look at some real life examples of exponential growth and decay. And what we've got here is, again, mitosis makes a comeback. One cell divides into 2 cells, where A, our exponential factor, is 2. Okay, and what we've got here is the graph of mitosis, which as the number of divisions increase, so too does the number of cells. And what we've got again is this exponential rate of growth, that this real kick point. The difference between, say, a linear function is as x increases by whatever it is, the y value always jumps by the same amount. But with exponential functions, you usually hit this kick point here where, I mean, I sort of say that the function just goes nuts. The y values just increase really, really quickly. Hence why exponential is used to talk about things that grow fast. We've got a bank, long-term investments with 10,000 invested at a rate of 2.4% per annum. So what we've got is 102.4% of the previous investment value. That is all of what we had plus 2.4%. And the exponential factor, or the A value, is that. And our start value is 10,000. That's what we put into the bank in the first place. What about decay? Well, this is the example of the car. Bought a car for $24,000, decreases or depreciates at a rate of 12% per annum. Our A value is 0.88. the start value is the initial value of the car, okay, which was, well, that should be 24,000, but anyway, so here it is over here. And what you note here, we've got the start value of the car, and as the amount of years increases, so too does the value of the car decrease, okay, at 12% of, or decreases at a rate of 12% of the previous year's value, or be careful here, 0.88% of 0.88 of the previous year's value. So essentially it's going down, okay, like so, but it follows this exponential decay path rather than the straight up linear path. Same thing happens with radiation. Radiation's got a half-life. So what happens is, whatever the thing that we're looking at, the amount of radiation in the substance or the amount of radioactivity in the substance will decrease by half. Okay, and so again, what you do is you start with the amount there, and then it will halve and halve and halve and halve and halve and halve, keep halving. Decrease in population by 2% per annum represents a 0.98 A value, or 98% of the previous year's population. So let's graph a couple of these. We got John investing, what is that, 100,000 at a rate of 14%. So note our value, this is our start value here, this is our A value, and this is our N number of years. So let's draw our graph of this. So what we're going to say is that our start value is the 100,000 that John invested. So that's where we're going to begin, and we're going to do a closed circle there. All right, we're going to jump over to our CAS here, and we're going to type in our function. So we've got 100,000 there, multiplied by 1.14 to the power of 1. So that's what he has after 1 year. Okay, is 114,000, so that would be whereabouts 1,100. So somewhere there. And we can then do the rest of this on our calculator. So you can go 2, 3, make sure you're in decimal, 4, and 5. So what I'll get you to do with your notes is to try and mark those key points as close as possible to where you think they belong. So I'm going to put the last one in there, 192,000 rather, 541, somewhere around about, well, there. Okay, now what you would have found is, so we are now going to attempt to connect these with an exponential curve. And what I generally find is if you plot the individual points, you'll kind of be out, like it just won't work. I'm just going to just sort of put some in, and what students do is they'll sort of try to connect up their points and draw your line that way. And what you'll notice is that your curve is going to waver around a fair bit. And so what you want to do with exponential functions is, I call it actually just cheat a little, okay? So I wouldn't actually go ahead and put all of those points in. I would put my 2 endpoints in. And generally speaking, what we do is we take these grid patterns off so that you don't have to commit to the values in between. And to draw my exponential function, I would bring it through like so and get it going through that point. Now, again, this curve needs to be really smooth. Okay, see how it jumps up, stays up, and then jumps back down. So again, practice drawing a nice, clean, smooth curve there, labeling your endpoints. So 5,19,541 point. Now I'm going to round this to 2 decimal places, and I'll explain why in a sec. 4, 6. And this one was 100,000. All right, now how did I know to label with 2 decimal places? Well, this is money. Okay, money is expressed at 2 decimal places. So this is a situation where it's implied rounding. So what effect did A, B, and C have on the shape and position of the graph and the equation of the asymptote? All right, our A value was 1.14. Our B value was 100,000, and our C value, it didn't go up or down, it was 0. Okay, our asymptote, because it didn't go up and down, would still be along this line here, where our asymptote equation is A equals 0. Note the context here, we've been using Y equals 0, but this one here is A equals 0. All right, so once we've got that down now, what effect did it have? So this A value here represents exponential growth, and this B value represents a dilation factor of 100,000. Okay, so it takes your original y-intercept, which would be 0, 1, and multiplies that y value by 100,000, which takes your point or your y-intercept all the way up there. All right, how much will John have in the bank after 3 years? So we'll go over to the calc, and there it is. So A equals 100,000 multiplied by 1.14 to the power of 3 equals 148,154.40 How long will it take for John's money to at least double in value? So what we're going to do is say that I want to know when John's $100,000 will become $200,000. Okay, so to do this one here, we're going to jump over to the calc and go a solve on that. So we're going to say, can you tell me the value of x that would make this side the same as this side? Okay, so this says n equals 5.29, which now raises a really interesting question, because how long will it take? Now note that when we pay out interest, according to this question anyway, the interest is paid out annually, which means that we can't actually answer the question with 5.29 because they don't give you interest in this question anyway in the middle of the year. So my answer is going to be, therefore, n equals, now this is a bit controversial here, but see if you can understand what I'm about to do. I'm going to put n equals 6. Okay, now why am I going to do that? Let's go back to the calculator to show you the reasoning. All right, so if I raise it to the 5, okay, so how long will it take? Notice there that I haven't at least doubled the amount. So after 5 years, I don't at least double the amount, okay? So it has to be 6 in this case. So it has to be after 6 years that I'm going to at least double the amount or get over 200,000. So a common mistake there from students will be to round n to the nearest year, which will be 5, but that simply won't be long enough for the value of the money or the value of the investment to double. Okay, and we'll do one more example representing Decay. So what we've got is a city of 50,000 people is, for whatever reason, decreasing by 12% per year. So what percentage of the original population after the first year? Not sure exactly what percentage of the original population after the first year. Don't know what that question is asking. Let's forget that. All right, so what we're going to do is sketch the graph. So this value here represents the dilation factor. So it's dilated by a factor of 50,000 from the x-axis. So our original y-intercept, which should be down there, gets multiplied by 50,000 to come up to here. Okay, and what's going to happen is, as n increases, we're going to get this decay. Okay, unfortunately, for whatever reason, this town has a decaying population. Not literally, but mathematically. So to sketch this graph, I'm going to do a very similar thing to the last one, which is to only sketch the endpoints. Okay, so I'm going to go up to an n value of 6, which is 23,220. So here it is here. This is 22, 24, 26, 28. So 22 is there. 23, again, it's going to be really hard to get this to scale. It's somewhere here. All right, now those of you who plot the points in between, again, what I find is when students do that, they'll get points a little bit out and then their curve is going to jump around, okay? So for these functions here, you want to just sketch the endpoints and link them up with a nice exponential curve, okay? Again, one probably dips too early there, so you probably swing it down. I'm going to have another go at this actually. I'm going to swing mine down a little bit faster, then gradually come into that point. Again, dips down there, I'm not happy with this. One more try. All right, save the best for last. That's not bad, that one. Okay, our asymptote. Well, because it's plus 0 on the end of that, it doesn't go either up or down, which means that our y-intercept or our y-asymptote, p equals 0. It doesn't move up or down. What effect did the values of A? So A was 0.88 from memory. Yeah. Our B was 50,000. Our C was 0. So this one here meant that we had exponential decay. So that's that shape there. This meant we had a dilation factor 50,000 from x-axis. What would be the population of the city after 5 years? So I'm just going to go to my calc and replace whatever I was doing there with a power 5. So this one will be P equals 50,000 times 0.88 to the power of, don't need to use that symbol, to the power of 5 equals 26386.595 ... Therefore, how many people, well, what we'll do is we'll round this to the, okay, so this is again a good discussion point, 26386. Okay, now, notice here how I rounded that. So I'm going to round to the nearest person, but see this 0.5 there. If I round up to 0.7, it'll be, ooh, no, what am I going to do? Okay, here's a good situation here. So I'm going to, so I've got the power 5 here. I'm going to work a little bit backwards on my calculator and go solve 26386 equals 50,000 multiplied by 0.88 to the power of x, comma x. All right, and so when it's 6, you'll note that this is after 5 years. Now, if I round that to 7, notice how I'm down to 4.99, which is not after 5 years, okay? Why wouldn't I give an exact answer? Because human beings are either there or they're not, so we can't have a decimal human being. We can't have 0.5 of a human being. So our answer to this one is 26,386 people. And often the way to work out how to round, whether you round up or down, will again be completely context driven. So 87, if I round it up, would keep me below 5 years. 6 will get me above 5 years. So you really do need to check your calculators on these questions to make sure that you're rounding according to the context. Okay, how long will it take, last question, to get to 40,000? So that's going to be a solve 40,000 equals 50,000 multiplied by 0.88 to the power of x for x. So x is 1.745 ... And I don't really know how to answer this one in terms of rounding. How long will it take? I think we're going to leave this as our most exact value here and say that it's going to be this amount of time, so this many years, because why would I not round this one? Because people, when they decide to leave a town, don't wait until December the 31st, New Year's Eve. Woohoo! Let's leave right now. They'll leave in dribs and drabs. Okay, so at this point here, we can say that, you know, like we might lose some people in February, some people in March, etc., etc. So we're going to leave this one as our exact value, 1.745. Now notice that continues on the calculator. This ... represents the fact that I'm not going to round this number here. All right, so have a look on Firefly now to work out what pages, what questions have been set for you. And as always, get in touch with your teachers if you need any assistance.